Okay, so before we move on to graphing rational functions, I've actually included a cheat sheet in your lesson for the week. This is a great sheet to have, to print out, to keep with you so that you can go through and kind of follow along while you work the problems until you become familiar with exactly the parts of rational expressions. So, everything that we have been doing with rational expressions, it all has a place on a graph. And that's what we're going to talk about now. So anytime we're graphing rational functions, of course, just like I said, we always factor and cancel out first, just like we did on the previous ones. Okay, now that part that you factored and canceled, right? That x plus, well, look at our example problem. We have x squared minus x minus 20 over x squared plus 5x plus 4. Now they put it into their factors and they canceled out x plus 4 over x plus 4. So that part that we cancel out, that x plus 4, well, it has a place in our graph, okay? That x value is the whole, okay? So the canceled out portion is the x value and it is the whole. Now, it is quite literally a hole on my graph. If you pay attention, see, I have a little yellow dot there, or I have a dot. That is a physical hole in my graph where nothing occurs. Why? Because it canceled out. Now, to figure out exactly where that hole is placed, we have to find that x value, right? Meaning we take that x plus 4, we set it equal to 0, and we solve to get a negative 4. Now, once we get that negative 4, we actually take it, and for step 2 and 3, you take that negative 4 and you plug it into your reduced function to get an answer so that you get, in this case, a 3 whenever you plug it in. So we have a hole at negative 4, 3 on our graph. So my yellow, all the highlighting of my yellow, that all goes together. Now, plug the hole. Okay, we're going to talk vertical asymptote. Let me change my colors for this one. All right, so the vertical asymptote, you take the remaining denominator, all right, that x plus 1, and he becomes your vertical asymptote. Okay, that literally means that you're going to take and you're going to create a vertical dotted line on your graph. Okay, and he is basically a barrier, meaning your graph is not going to pass that, that value on either side. Okay, so the vertical asymptote is the remaining denominator. So remaining denominator. Now the x-intercept. Well, the x-intercept, all you have to do is take the remaining factor in the numerator, make him green. That x minus 5 that you have left over, he is your x-intercept. You're going to set him equal to 0 and you're going to solve, and you actually will cross your x-axis at that point. Okay, so your x-intercept, you take your remaining numerator. Your y-intercept, you take and you plug a 0 in to your function, or your expression. Oh, no. Sorry, guys. Okay. So the y-intercept, you plug a 0 in and you get your answer. In this case, we say it's at negative 5, so that we know we are going to actually have it's going to cross our y-axis at negative 5. Now, we have to talk about the horizontal asymptote. If we have a vertical, we're going to have a horizontal. And all we have to do, let me choose a different color. I'll go orange. Now that in behavior, well, that's controlled by our very first term, okay? So the in behavior, that for our horizontal asymptote, actually, we take and we look at the values in the front, okay? So in this case, I'm looking at my x squared over x squared. Remember, if there's nothing there, I hope you understand, it's an understood 1. So if we take a look at that bottom little chart, I have my, you can think of this as the end behavior asymptote, or it's also known as the horizontal asymptote. Okay. Now, if it's x squared over x squared, meaning they're the same, it's going to be a 1. Meaning you're going to have a horizontal line at 1 on the y-axis. Okay, remember, it's like dropping that x squareds so that you get a 1 over 1, which equals 1. Now, looking at the next one, I have an x and an x. They are equal to each other. So again, all I have to do is drop the x's and just work with the coefficients in the front so that I get 2 over 1, which is just 2. So I know I'm going to have a dotted horizontal line at 2. Now in this case, again, I have an x over a 2x. They are identical to each other. So I know I'm going to drop them so that I get 1 over 2, which is 1/2. Now the only time that you're going to end up getting 0, right? If we look, we have an x over an x squared. They're not equal to each other. So we know by that alone, we're going to have a different end behavior. And in this case, it's going to be 0. Okay? So these are just little ways to help you take the parts of your rational expression and utilize them to find the different pieces and the graphs and everything else. So we're actually going to take a look at our next set of questions. Now, it says, look at the graph. Together, you're going to label the vertical asymptote and the horizontal asymptote. Well, that should be nice and easy. I'm looking for my dotted lines, okay? So my vertical line for this guy here, I'm going to take and draw my little red vertical line. He goes through x equals -2. So I have a vertical asymptote, because he has a vertical line, at x equals -2. Now I'm going to find my horizontal line. I'm going to double check where he goes through. And in this case, I have a horizontal asymptote at y equals 2. Okay, so it's very important to pay attention to the scale as well. Now, this one's slightly different. Okay, so my vertical asymptotes, I have 2 of them, right? So I actually have 2. I have one that goes through -1 and one that goes through +1. So I have 2 vertical asymptotes, and I have it at x equals -1 and x equals 1. Now, I don't have a horizontal dotted line, but if I pay very close attention to the end behaviors of my 2 graphs here, I notice that they get really, really close to that x-axis, but they don't actually cross it. So he ends up becoming my horizontal asymptote, okay? It's where your graph gets really, really close, but he never actually crosses. So I have a horizontal asymptote at what ends up being y equals 0. Remember, the axis is y equals 0. All right, next one. Vertical line, I'm going to pay very close attention to my scale. It looks like I have a vertical asymptote at x equals -3. I have a horizontal, if I pay attention again, I have a horizontal asymptote, and it is at y equals -1. Now, in our notes, it says vertical asymptotes are used to show domain restrictions. This comes in importance whenever we go to write our end behaviors and our domain in our range. Okay, it says the graph of a function will never cross a vertical asymptote. Okay, so your graph will never cross the vertical asymptote. Now, looking at 4, it says what are the domain restrictions for each of the following functions? Well, we can figure that out pretty quickly. All we have to do is take and only pay attention to our denominator. So all we have to do is factor the denominator. In this case, I'm going to say what times what is -4, but adds to be a -3. Oh, hold on, guys. I know that I have to do, it's going to be what, x minus 4 and x plus 1. I set those equal to 0 and I solve and I get x equals 4 and x equals -1, which means that those are going to be my restrictions. So x cannot be 4 and x cannot be -1. If they were, well, then I would get 0 in the denominator, and I know I cannot get 0 in the denominator. So those are my restrictions. All right, B. Again, I need to know my factors. So what times what gives me 15, but adds to be 8? Well, I know it's going to be x plus 5 and x plus 3. I solve, and I get x is -5 and -3. But in this case, because it's in the denominator, I know that it cannot be those numbers or those values because you cannot get a 0 in the denominator. So, looking at our notes, it says the horizontal... Come on. There it is. Okay. The horizontal asymptote of the graph of a rational function is used to indicate end behaviors. Now, it is possible that a graph will intersect a horizontal asymptote. Okay, so it will intersect a horizontal. It will not a vertical. Okay, so it usually does this around the middle of the graph. Now, if we were to take and go up to question B, you will notice that it crossed in the middle. Come on. You notice that it crossed in the middle of our graph right here. Now it says the graph of a rational function will get very close to the horizontal asymptote when the x values of the function are very large or very small. So now we're actually going to take and utilize a lot of it. Let's see, let's go over to our next set of problems. Okay, so question 5. It says, find the domain, the horizontal asymptote, and the vertical asymptote. And we're also going to determine if each of the rational functions have any holes in the graph. Well, what does that mean? First, I need to figure out what my denominator would be. Okay, so for A, I look at it, I have 1 over x plus 1 minus 4. I actually don't need to solve this problem or really work this problem. What I need to know is, are there any holes? Does anything cancel out? In this case, if I were to create a common denominator, right, of x plus 1, has to be x plus 1. Nothing ends up canceling any out, so I know I'm not going to have any holes, but I am going to have to take that denominator. Sorry, guys. I'm going to have to take that denominator, x plus 1. I'm going to have to set it equal to 0 and solve so that I get x cannot equal -1. Because if it did, I would have a 0 in my denominator, and I cannot have that. And because if I were to work this problem out, nothing would cancel out top and bottom, so I know there are no holes. Okay, now B. I am going to have to factor. I have x minus 1 on top. I know that x squared minus 1 is the difference of squares, so I get an x minus 1, x plus 1. I can cancel out x minus 1, x minus 1. Well, that means that x minus 1, if I set them equal to 0, I have a hole at x equals 1. So I do have a hole. But I have to take and find out where that hole exactly is located. Not just x equals 1. I actually need to take, and I need to take that reduced problem. Whenever I cancel out, I know I get a 1 on the top and x plus 1 on the bottom. To find that hole, I'm going to have to plug that 1 in, so that I get 1 over 1 plus 1, which of course is 1/2. So I have a hole at 1, 1/2. So at 1, 1/2, I will have an actual hole in my graph. Now, I need to take that remaining denominator that I got, that x plus 1, I set him equal to 0, so I get x cannot be -1. So I have a hole at 1, 1/2, and it cannot be -1, meaning I have a vertical asymptote at -1, right? This is the vertical asymptote. That is the hole above it. And in this case, my horizontal is going to be 0. Right? Remember, if I had an x over x squared, if I paid attention to my cheat sheet of in behaviors for horizontal asymptotes, I look and I see, oh, it's x over x squared. I have a horizontal asymptote at y equals 0. So I'm actually going to put y equals 0.